Good afternoon, everybody, and welcome to today's IMechE webinar on a net zero future for UK manufacturing. My name's Sam Turner. I'm the chair of the IMechE Manufacturing Industries Division, and part of our mission within the division is to raise recognition of the importance of manufacturing in creating sustainable economic growth and rewarding careers. Now, a really important part of that focus is looking at the role that manufacturing engineers play in addressing global challenges and looking at the profile of the future manufacturing engineer. In particular, looking at the challenges that we face and the role that we can play in addressing the challenges around the environment, and particularly the government's commitment to net zero for 2050. So we recognise that there's a great chance for us as a community and for the UK to pioneer the development of solutions and technologies and raise the profile of manufacturing engineers, to see us as not the community that pollutes and contributes towards the problems of the environment, but actually those who can pull together and create the solutions. So really looking at the engineering community, in particular manufacturing engineering, as the community who can address the challenges that we face as a nation. As part of my day job, I'm the Chief Technology Officer of the High Value Manufacturing Catapult. Now, we're an R&D organisation. We've got about 3,000 engineers over a number of sites across the UK, working across all sectors. And we work in scaling technology from the technology and academic base to develop solutions that drive prosperity, de-risking them and drive prosperity of the UK manufacturing and engineering community. So at the High Value Manufacturing Catapult, we're focused on, as well as supporting UK prosperity and growth, we're very much focused on the net zero emissions targets for the UK, and in particular looking at those related to transport, to energy, the energy mix, and of course manufacturing, delivering resource efficient manufacturing. Now, depending how we look at the mix, if we consider the contributions made from our imports and the manufacturing footprint that we have around the world, up to 30% of emissions that could be attributable to the UK relate to manufacturing. So it means that the resource efficient manufacturing is a crucial part of the solution we need to address to meet UK's challenges, but also a chance to develop innovations, technology solutions that are exportable, that actually mean we can make a much greater impact than just the UK direct emissions by showing leadership in developing these solutions. Another option, of course, is to say that imports don't matter and that we can move away from manufacturing outside of the UK. But that, of course, doesn't really hit the lessons we're learning currently about resilience or about economic and social balance. So there's a great chance to lead the way in reduction of emissions globally as an engineering community and as a nation. So we've been working very closely within the Catapult with Professor Julian Allwood at the University of Cambridge and Julian's UK Fires Consortium. The report that was produced at the end of last year, Absolute Zero, has had a huge impact in leadership, debated in the House of Lords. And Julian and his team have provided a really strong voice and clarity of thinking around difficult choices that we face in delivering net zero, both in terms of societal and behavioural change, but also in the innovations and challenges we need to address as an engineering community to deliver those solutions. So it gives me great pleasure to introduce Julian to take you through his excellent work and today's presentation on a net zero future for UK manufacturing. Julian, the floor is yours.
Thanks very much, Sam, and hello, everybody. I'm delighted to have been invited to give the talk and to share the platform with Sam. It's a real pleasure being able to collaborate on this. As Sam said, I'm speaking today as Director of the UK Fires Programme. This is a £5 million 5-year research programme funded by the Research Councils via BAYES, spanning 6 universities. And our title is an acronym for placing resource efficiency at the heart of the UK's future industrial strategy, if you can work that out. So I thought I'd start by talking briefly about resource efficiency, where, if you like, there are two possible concerns that any of us could have about resources. One is about the possibility of shortage. Are we going to run out of things? And sometimes that's referred to as criticality. And the other is about the impacts of processing. And if I think about that, then the idea of criticality, which has come up a lot, particularly for the technology metals, turns out always to be an issue of timing. We aren't actually running out of anything. And if you think about the principle of conservation of mass, then apart from in nuclear reactors, we don't destroy any mass. So all of the atoms available to us remain there. But there is sometimes a question of timing, because it takes a while to open new mineral supply sources. So our understanding of criticality is really about the amount of spare capacity in the materials supply chain over or related to the possibility that demand may make a sudden jump. So if demand jumps or capacity suddenly constrains, we have a problem of criticality. But essentially it's always temporary. We can always compensate by adding more capacity. The other issue about shortage, which is a real one, is that as we have mined the easier to access deposits, then it may mean that we then have to access less concentrated deposits in future. And I think that's happened, for example, with bauxite. So the amount of energy required per ton of alumina extracted from bauxite has actually gone up in the last 3 or 4 years, because we're having to mine slightly less concentrated deposits than before. So criticality is a timing issue, and the idea of less concentrated deposit relates to having more energy. If I go to the other part of my branch on the impacts of processing, then obviously some of those impacts are about pollution, whether it's to air, water, and soil. And traditionally, these forms of pollution get resolved once there is a sufficient middle-class lobby to persuade polluters that they ought to change their behavior. So water quality in rivers in the UK, in Western Europe, is very good. Water quality in Chinese rivers is improving, depending on whether there's a sufficient lobby locally to impose improved standards on the polluting body. But the other form of impact is, of course, greenhouse gas emissions. And some of the big processes release greenhouse gas emissions by their chemistry, for example, in blast furnace making of steel or in the production of cement from limestone. And most of the energy-intensive processes are depending on fuel consumption. So in effect, the two green issues that I've highlighted here, more energy for more concentrated deposits or the release of greenhouse gas emissions through fuel combustion or through the chemistry of reactions, come down to the same thing. So for me, the issue of resource efficiency turns out to be the same as the issue of reducing greenhouse gas emissions to a safe level. And therefore, today's talk is going to be about a zero emissions future for UK manufacturing. It's particularly motivated by the fact that the UK's law changed last summer at the end of what was possibly an unhappy period of 3 years as Prime Minister. In her last month, Theresa May did something fantastic and surprising. She responded to the school strikers and the social protesters about climate change wanting faster action, and proposed that the UK's Climate Change Act, which had been a commitment to cut our emissions from 1990 levels by 80% by 2050, she changed that to being 100%. And remarkably, that went unanimously through both houses of Parliament in June last summer. So it is now the law in the UK, unanimously approved by all politicians, that we should have zero emissions by 2050. And that's extraordinary as a law. It turns out in retrospect that when the law said that we should have an 80% cut, then in effect everybody thought that they themselves were in the 20%, so somebody else should take the impact. But with a 100% cut, there's no escape. It sets an agenda. And I think it's worth commenting that we're not on our own there. Finland has a target, a law to get to zero emissions by 2035. The EU is currently debating getting to a 95% cut by 2050. I think that's likely to go through. California has an 80% target. Under Obama, the USA's target was about a 76% cut. And India, I think, has passed a very sensible law for a developing country, which is that they will hold their emissions per capita lower than the developing countries. So that for a developing economy, I think places the burden right back on us in the developed economies to set a standard to which the developing economies then aspire. So we're not on our own, but we have a very striking and stringent target. The first thing to say about that target is that it's being discussed, and we use the phrase in our title for this talk, as net zero. But net zero implies that there are some negatives. And in effect, there aren't going to be any significant negatives available to us by 2050, or at least it's extremely unlikely. So to put that in perspective, firstly, we often talk about the idea of growing more trees as being an important contributor. And it is. But once a tree exists, then it forms part of the natural carbon cycle. So a tree grows, it captures CO2 by photosynthesis, but then when it's cut down and either burnt or it rots or post-use it's disposed of, then all the carbon in the tree gets released back into the atmosphere. So an established forest is in effect part of a net zero emissions cycle. If you want to increase the amount of CO2 stored in wood, you have to increase the area of forestry. And to put that in perspective, if we doubled the total area of forest in the UK in perpetuity, so we took land that currently isn't forest and we guaranteed that it would be forest forever, then the total effect of that would be to capture just 2 years of the UK's current emissions. So that's a significant effect, but it's not a very big one. It certainly doesn't remove the obligation to achieve zero emissions. The two other technologies that are being discussed most for having a negative effect are direct air capture. But if you think of that within the frame of reference of the second law of thermodynamics, then it's obvious that it's always going to take more energy to take carbon out of the atmosphere than was released when we burnt fossil fuels to put the carbon there in the first place. So it would only make sense to do that if we had spare zero emissions electricity to power the capture. And until we're at that point, it would always be better to replace other uses of fossil fuels with renewably powered electricity than to waste them doing direct air capture. So in the short term, i.e. in the next 29 years, that isn't going to be significant. And the last option, which remarkably features prominently in the many climate mitigation plans, is BECCS, or bioenergy carbon capture and storage, which currently isn't operating anywhere, and we don't know how that's going to work. We know that some emissions will be inevitable from it anyway. And if you think about it, then burning wood and then capturing the emissions and burying them underground doesn't actually lead to any sequestration of emissions until more trees have been grown. So even if we suddenly had a supply of BECCS plants operating today, their effect in reducing emissions would only occur once new forestry had grown sometime into the future. So I think it's rational to plan that by 2050 there really won't be any negative technologies, and that means that net zero actually means absolute zero, or as Greta Thunberg said earlier this year after we put our report out, real zero. I'm happy that either real or absolute zero mean the same thing. So our target then is absolute zero, and before we think about what that means, the key question is, are there going to be new technologies that significantly change our position between now and 2050? And all government policy so far in the UK has assumed that new technology is going to have a significant effect. and in particular that we'll be able to find sources of energy that have no emissions associated with them. The most prominent of these is always carbon capture and storage applied to fossil fuel electricity generation plants. There are some of these operating in the world at the moment. We know from the oil and gas industry funded lobby that supports them, the Global CCS Institute, that the total capacity of installed CCS plants is equivalent to 0.1% of the world's anthropogenic emissions, those caused by humans. But what we don't know is how much of that capacity is being used. If you read the reports of the Global CCS Institute, you'll see that they cleverly switch between the words capacity, capture, and storage, using the word storage very rarely, because even those plants that are being developed and operated, in many cases capture CO2, but then release it because the storage component of the supply chain isn't yet operating. So what are the odds that new technology will be playing a significant part by 29 years ahead of now? One answer to this is to look at the recent past. And I've got a graph here, the web system is sometimes rather slow to show me the next graph on my slides. Okay, I'm unable to show you the large version of the picture at the top left here. That shows you 4 energy transitions in the 4 countries which delivered the transition fastest. So the top one is nuclear power in France, then wind electricity in Denmark, CCGT in the UK, and solar electricity in Germany. And the graph starts at the point that the technology was first demonstrated at some meaningful scale. The blue graph describes the period of market development, of technology development, getting up to the point that the full-scale system was ready for being deployed at wide scale. And then the red bar shows the period of market development when the legislation, the forms of infrastructure, the environmental regulation and so on was developed. And the green arrow indicates the point at which mass deployment began, not ended. So you can see there that the period of development was between 30 and 50 years from the first development of the technology to the point at which mass rollout actually occurred. You can see that graph on the right-hand side of the slide in front of us now, which shows on the right-hand side the story of wind electricity generation in Denmark, growing from 0% to about 40% of Denmark's electricity requirements now. And that's after the first wind turbine generating electricity was demonstrated in the US in around about 1930. The wind deployment of the worldwide deployment of wind for electricity generation, you can see, is still growing quite rapidly, but that's because it's an earlier stage of the market. It's only reached 4% of total electricity supply in the world at the moment. So what that suggests is that if we have a new technology such as carbon capture and storage, which has been demonstrated only at very, very small scale. In fact, there's only one power plant that's had it attached at the moment, the Boundary Dam project in Saskatchewan, and they don't publish data for what they've captured and stored. Then the evidence from past transitions is that it's going to take a very long time before that starts reaching major deployment. To make that point a different way, we often use the technology readiness level scales when we're thinking about introducing new technologies to the market. And the end of that scale, which begins at TRL1, which is somebody having a bright idea on the back of an envelope somewhere, TRL9, technology readiness level 9, is when the technology has reached full scale and is ready to be sold into the market. But that's not the point that we're aiming at when we think about global carbon mitigating climate change. We don't want the first deployment. This is nothing like the Manhattan Project or the space race. What we need is market saturation So it doesn't matter when the first one enters the market. What matters in reducing our total emissions is when a technology has completely replaced the technologies that are being used today. It's a very different point to TRL 9. And it takes a long time, as that graph shows. And of course, there is an engineering explanation for this, and it lies, I think, in the heart of civil engineering. The picture I've put up now is of the new Queensferry suspension bridge in Edinburgh, which was initiated in 2004 when road engineers reported to the Scottish Government that the previous bridge had lost 10% of the strength of its cables, so needed to be replaced. So the Scottish Government deployed that project as fast as it could possibly occur, and it took 14 years to open the new bridge. That's a completely more mature 200-year-old technology, but even so, building it took 14 years. And the first 8 years, no spade hit the ground. That was all about consultation on finance, on land acquisition, on environmental protection, on legal issues, and so on, all of which is actually necessary. It has to happen. And of course, this will have to happen with any new energy technology as well. So there's an engineering reason why new energy technologies can't be deployed at great speed. And we just can't pretend that magic technologies will appear out of the air, be invented and deployed at the level of market saturation within 29 years, or at least it would be a very highly risky thought to do that. And I want to make one final point about new technology in the light of the virus, which of course is very much on our mind at the moment. I don't know if you're aware of it, but over the last 20 years, a whole range of people in medical research have been receiving funding for projects under the banner of vaccine in a day. And you can imagine how easy it is to write the funding proposal for research on that. It says, the world is under great threat that a pandemic will occur, but we've got an idea that will allow us to use the latest DNA, gene sequencing, etc., 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 and we'll be able to produce a vaccine for any virus in 24 hours if only you fund our research project. Well, lots of people have had that research funding, and as we now know, the technology wasn't ready. So instead, we had to move to a lockdown because we hadn't made preparation for other forms of response to a pandemic. The graph I've put up here is a thought experiment for something that we're developing in our research group at the moment. In the world of investment, and I think the computer trading algorithms that are used for share trading in the city, think of a frontier of risk when they're trading. And typically they have one axis which is about the volatility of the share price and another axis which is the underlying growth in the price. And out of that they have a risk-reward profile of all the shares that they could trade. And they try and position their portfolio along the efficient frontier, which I've represented by this red line. So if I imagine that in our case the axes are the risk of technology uncertainty against the reward of social disruption, or I suppose the positive is avoided social disruption, then you can see that the image I'm showing here is that the preparation for the pandemic was to focus on high technology solutions, the vaccine in a day, but not to think of forms of preparedness like spare manufacturing capacity, spare PPE, spare capacity in the NHS to be able to respond to the unexpected. Well, you'll imagine that I put that up in order to draw an analogy with how we're preparing for climate change. That almost all funding and policy, both nationally and internationally, is focusing on these miracle technology solutions, particularly around variants of carbon capture and storage, which are high risk in the sense that they currently have so little impact on the international market, and have the attraction, which is why they're being pursued, that if they worked, they would have little social disruption. But in fact, if they're not ready at the point that we decide we really have to act rapidly, then instead we'll switch to having a blackout. We just won't be able to operate because we won't have enough power for the way that we live at the moment. But there are many things that we could do to be more prepared. And I think that's really the point of our work in the UK Fires Consortium, is to raise awareness of the wider portfolio of options that we could be developing, knowing that many of them will have market value, even if the magic technologies of CCS and so on are developed faster than we expect. But if they're not developed, then they're going to be essential at the point that society asks us to act very rapidly, because the impacts of climate change have become so unavoidable and threatening. So that's the background to our report on absolute zero. And on the front cover, we used a little graph like this to say we know that by 2050 we want our emissions to reach zero. That's now set into law and unanimously voted through by all political parties and both houses of the House of Parliament. And so we should anticipate that what that means is some reduction in our energy availability as we find energy that's compatible with zero emissions, knowing that later on, innovations such as CCS and electric aeroplanes and all sorts of other things will happen, but it's unlikely that they're going to have reached market saturation within 29 years' time, and foolish to plan on that basis. So that was the basis of the icon that we used on the front cover of the report. And if you're interested, you can download it from the UK Fires website, which is in the footer to these slides. So to develop our analysis of what the UK's law now says, we looked at the history of how we've been generating electricity in the UK in the last 25 years. And you can see that graph now, and you can see that our emitting generation from the fossil fuels has declined, and the upper blue line, our non-emitting generation, has grown, particularly due to an expansion in wind and most recently in offshore wind. So as we're all engineers, we can look at that blue line over the last 10 years or so and say, well, that's pretty straight. So let's anticipate that that rate of growth in non-emitting generation continues for the next 30 years. That's not trivial, and it requires more than meeting the current set of licenses for offshore wind that the Crown Estate has released for the North Sea until 2035, as well as Hinkley Point. We'd have to anticipate there might be more nuclear, and so on. So it's a big commitment to get that degree of non-emitting generation grown. But we've got a history there, so let's just take that straight line forwards. And then we can predict that our electricity supply in 2050 will be all non-emitting, and it will be 1.6 times greater than we have today. If we've removed all of our emitting generation, then we'll have about 1.6 times more electricity than we have today. And that will be our only energy supply because we'll have cut out all of the fossil fuels by then. So to get an idea of what that means, the first thing you have to do is to work out how much energy we would need if we electrify everything that we do in the UK today. Converting electricity into motion in an electric car, for example, is very efficient compared to converting petrol into motion. So we did an estimate based on some pretty good data of the way the UK delivers services from goods that consume energy at the moment. And we made a calculation of what it would take to, if we electrified everything, and provided we exclude the four things that we can't electrify and remove emissions from, then we end up with the top of our buildings bar there is around about 1.5, 1.6 times more than the amount of electricity available. So in other words, we'll have about 60% of the electricity that we'd like to have if we electrify everything that we do today, which doesn't sound too bad. But we have to take account of the fact that there are four things that we can't electrify and remove all emissions from. I'll come on to those in a moment. And as Sam mentioned earlier on, our recent history of emissions mitigation has involved closing industry and claiming that's a success as our balance of trades in goods has worsened dramatically. And of course, importing goods from emitting countries elsewhere does nothing for global emissions. So that's an artifice that we very much want to counter. So what does it mean to live with 60% of the energy we'd like? Well, we looked through all the major energy using activities. So for example, here's energy used in buildings in the UK. The left-hand bar shows all energy uses in buildings today. Those above the horizontal line are electricity or losses, and those below are powered by fossil fuels, mainly gas, of course, for heating, air and water, and for cooking. So the second bar says what we would need if we electrified everything, and you can see that we would need more electricity than available if we took a fair share of the 60% supply we'll have across all sectors. So could we reduce that to 60% either by behavior or by technology transitions? And if we're lucky, the next component of my slide will now come up. I'm afraid the webinar system is letting me down again. There's, yeah, I'm sorry. There we go. I hope you can see the same screen as I can see. Figure 2.3 on the right there shows that there are various technologies that already exist that we could deploy at scale, like replacing boilers with heat pumps. And we've assumed at the moment that that's just a water-based heat pump system. We haven't replaced the radiators. We could pursue existing known options for appliance efficiency, make sure that all new build houses are passive, and so on. So we could easily get to the 60% target with known technologies in the buildings, or of course we could do it by behavior change. So simply by turning on the air and water heating for 60% of the time, by avoiding having any heat in rooms where people aren't currently sitting down, for example, then there are options that would get us down there. So across all the sectors, our estimate was that it's technically and socially feasible to live well with 60% of the energy that we need if we electrified everything today. But there are 4 activities that we can't electrify and get rid of the problem. The first of those is shipping. There are some electric ships, for example, operating short journeys across the fields in Norway, which has a very large low-carbon electricity supply. But at the moment, there aren't any electrical freight ships. Potentially, we could have them. We know that there are nuclear-powered warships, and it's possible, as I said, to have some battery-powered electric ships, as we have in Norway. But at the moment, we don't have any intercontinental cargo that's powered only by electricity. So that's problem number 1. Number 2 is aeroplanes, which are a much worse problem than is admitted in the UK's figures at the moment. The Climate Change Act has been written with a rather clever get-out, which means that we don't currently report international aviation, even though obviously that dwarfs domestic aviation. And the government does produce in its emissions report an estimate of the CO2 emissions from international aviation. But all of the climate scientist research shows that the impact of emissions from aeroplanes at height is significantly greater than other CO2 emissions. They have more global warming potential, roughly speaking, double. So if you take the government's figures for the total global warming potential of flight, and you include the government's non-reported but calculated figures for international aviation, then flying actually is about 12.5% of the UK's current production-based emissions, of the emissions caused by things that occur or are fueled in the UK. It's of course true that there are some electric aeroplanes. Somebody flew one person around the world in a solar plane a couple of years ago, and no doubt a small aeroplane will take off powered by batteries. But again, that's not what we're aiming at. To replace existing aviation doesn't mean one plane flies once. It means replacing all aeroplanes with electric planes within 29 years. And there is no possibility. Nobody currently has a plan for an intercontinental large plane powered by batteries. There are synthetic fuels being discussed, but the amount of energy required to make them and the amount of biomass to make them is so high I find it implausible that we'll be able to spare the resource to do that. So aviation is not compatible with or fossil fuel powered aviation is not compatible with our law on zero emissions, and it's very unlikely there will be electric substitutes within 29 years' time operating at full scale. In our eating, then the key change is ruminant animals. We can't currently grow sheep or cows without them burping methane from the front of their two stomachs. Maybe in due course new forms of feed or modified animals will be developed, but for now we can't allow lamb and beef. It's not compatible with our law. And the final one, which is really killing, is that we currently don't know how to make cement without emissions. Of course, potentially cement could be linked to carbon capture and storage in the future, but that links back to the problem I said earlier on about the scale of deployment. But we don't have any other binders, and that has a devastating effect for construction. So, zero emissions from our absolute zero perspective means electrify everything, cut the total demand to 60% of what it would be otherwise, and eliminate 4 activities: ships, aeroplanes, ruminants, and cement. And it sounds tough, but actually that's the law passed unanimously through both houses of Parliament. So interestingly, when this was debated in the House of Lords, they had a full 3-hour debate. The most common response was, you can't tell the public that, they won't like it. Which is an odd one, because of course we weren't telling the public anything. What we were just revealing was what their lordships had voted for unanimously when they put the Climate Change Act in its modified form through Parliament last June. And reflecting on all the reactions that we've had to the report, I put together this graph, which I think is helpful in understanding all the options for response. So my 2 main axes, incidentally, I did an MBA at a period 20 years ago when I was having an unhappy time in my life. And I learnt in an MBA that to make any management breakthrough, you have to have a 2x2 matrix. So that's the thinking behind this. The x-axis points between the solution arising from incumbent institutions or from transformation. And the y-axis says that climate change is primarily a public risk at the bottom or a private risk at the top. And out of those 2 axes, I've developed these 4 forms of solution. Techno-optimism, which is what I started with and which is what concerns me. For people who think that incumbent players will solve the problem and it's a private risk, then in effect what we're seeing is denial. And I think you can see that in the UK aviation industry announcing that they were going to be net zero. They announced that in February. The new chief executive of BP announced that BP were going to be net zero. Almost everybody is making an announcement of that type. But of course, behind it, there's either no plan or the plan depends on somebody else coming up with a new technology at major scale. So I fear that that's a form of denial. In the top right box, the social protesters and the school strikers are absolutely rightly pointing towards urgency, seeing climate change as an issue of ethical responsibility, and their goal is to try and motivate us towards making more change. But in the end, where we want to get to is the bottom right, where climate change is an issue of health and safety. And exactly as we have with asbestos now, nobody would imagine the government repealing asbestos legislation because it was holding back business growth. There would be a public outcry. And ditto with the virus, once it became a critical health and safety issue, it turned out that we were able to accommodate very rapid and wide-scale change because of concern about the impact it would have both privately and collectively on our health. So that's where climate change really belongs. And I think what we're aiming for is to help move or open up the portfolio of solutions that will help us move more rapidly into that box. So for now, I think we have to be very careful about the number of reasons that incumbent institutions come up with not to act on things that have a social impact, because the solution or the need to act is too important not to engage everybody in the process of change. Well, I want to finish off by trying to reflect on what absolute zero means as an innovation opportunity. When we presented the report through SAM to the catapults, then the CEOs of the catapult system replied not to challenge us on the basis of the report, but to say, gosh, that's interesting. What does that say about the innovation opportunity in the UK? And of course, it points to a tremendous opportunity for innovation, which, if we're right, and if the technologies that will take the problem away aren't operating at scale within 29 years' time, then that innovation is going to be mainstream business within 29 years' time. And if we're wrong and the new technologies arrive faster, then I suspect that all of the innovations we can point to that are compatible with our techno-pessimistic view are going to turn out to have market value as well. So that's the focus of all of our work now, is to think about where the opportunities are for UK manufacturing, compatible with our analysis in absolute zero, where we can see significant growth. So let me try and get a few pointers to that. Firstly, if I compare our anticipated demand for goods with the compatible supply, then you can see that the demand for cars and trucks overall has to be 60%. Now, it could be 60% of the weight, so it could be the same number and they could be smaller, because obviously the fuel consumption or energy consumption of cars is primarily driven by their weight. So it could be the same number of cars and smaller, or it could be a smaller number of cars of the same weight. But if they're all going to be electrified, and that's already the law, we've said that by 2035 we can only sell electric cars in the UK, then that points to obviously a massive growth in the whole supply chain for electric car batteries, including their post-use, which is a big open opportunity. And the charging infrastructure, I think, is a really, really interesting opportunity. It's striking to me that the oil majors are trying to propose the idea that petrol stations are a good place to distribute electricity. It isn't at all clear to me that that's the case. Petrol stations are located at convenient points for people who've already started a journey, but charging an electric car takes time. So actually, the innovation opportunity is to link the charging infrastructure to car parking. And I think there could be a major commercial opportunity for the first big car park operator who gets that. And of course, for the supply chain that supplies them with the goods. As we stand, then fossil fuel planes and ships will be illegal. So that market is going to disappear. There is, of course, an innovation opportunity for other forms of propulsion for both types of vehicle. Construction, then our analysis is pretty devastating, because without a binder, then there is no cement, and we currently don't know how to make cement at scale to allow construction to continue. So that says that construction is going to reduce significantly, or new build is, but vertical extension of existing buildings using non-cementitious materials is going to turn into a very big market. We won't have any blast furnace steel, but the opportunity for steel recycling is going to grow. And we've been pointing at that for a while now. We know that globally, even if we ignore climate change, there are more blast furnaces that we'll ever need again. But we also know that the supply of scrap steel is going to treble in the next 30 years, because we know where it is. All the steel that's ever been made always comes back for recycling. So there's a huge opportunity for developing upcycling through steel recycling processes and the supply chain around that. We know that the electricity generation is going to grow. There's going to be lots of big opportunities around the grid and new forms of distribution and control. Renewables are going to expand, and the fossil fuel industries are going to close, and so on. So there are some fairly obvious opportunities, I think, there. And if you chase those up the supply chain, then it says something pretty striking about the material supply. So obviously the fossil fuels demand will go to zero. It'll be illegal to sell them. The same for iron ore and for limestone, if the only use of limestone is for making cement in conventional processes. But in contrast, then our demand for the technical metals is going to grow. Biomass demand is obviously going to increase. And who knows with the light metals what's going to happen. Presumably demand is likely to expand for them if we have enough spare electricity to power their processing. We know that the sunset industries, fossil fuel extraction, processing, distribution and supply will be illegal. They're going to shut. And we know that fossil fuel aviation, shipping and so on are all going to shut. They're illegal or will be illegal in 29 years' time. However, we can see demand's going to grow rapidly for generation, for electrification of everything, and of course for efficiency. Efficiency in transport really means the size and design of the vehicle, but in buildings we know what the implementation technologies are. And to my taste, the biggest vote for the infrastructure spending splurge that's likely to occur out of the virus lockdown, then the key there is that the infrastructure projects that the government funds are about building retrofit rather than about new roads and rails or, for goodness sake, airports. What we need is to use that opportunity of investment to really focus on the existing building stock. But I think if we look a little bit wider, we can think of a whole range of other forms of innovation that are going to grow. And that's where we're really trying to focus our attention now. Obviously, material supply chains are going to change rapidly. And what we're thinking of as the scrap market is going to turn into the primary supply. But there's also the opportunity for substitutes. So we've seen in the last 6 weeks that our previous attitudes to remote working, virtual communications have been totally transformed. I hope that that's going to be the kick point for the change in attitudes towards flying, given that it's got to go anyway. But the opportunity to improve on virtual communications is extraordinary when I compare the level of graphics in Zoom compared to the level in an Xbox. I can see no end of opportunity for innovation there. Obviously, we're all thinking about more localized supply chains now. I've mentioned vertical extension of buildings, and if construction is going to be as difficult as we've said, then we're going to be looking at much more flexible uses of less space. Again, as we've all done, as we've learned to work in our houses in the last 6 weeks period. I think also there are probably other forms of innovation that are likely to come out of the lockdown. One of them is about resilience. We've been shown that the system that we had, which had chased a particular version of economic efficiency, turned out to be looking at unit cost, short-term unit cost minimization, but to lack the resilience to respond to an unexpected change. I think that's going to cause us to plan in a different way and to design our manufacturing system. And let's hope to trigger more of a renaissance in the UK. But I think it's also going to change our attitudes towards job design and lifestyles. The idea of participation and community, the social elements of work are much more important to us than we realized. And I imagine that we'll be going through a redesign that's not just about infrastructure and employment in the conventional sense, but actually about the shaping of the lives that we want to have post-lockdown. So to conclude or summarize, zero emissions is the law, and it's unlikely that it's going to be eased by new technologies. That doesn't mean that we shouldn't develop them. We should develop them like crazy, because it would be tremendous to have them there when they arrive. But kidding ourselves that the first installation means that market saturation will occur within 30 years is very, very high risk. We should be trying to take a more balanced view of the risk of our opportunities. And the severity of the resulting analysis, to my taste, reveals an absolutely extraordinary, fertile area of innovation and growth opportunities. I've pointed to a few today. We're trying to populate 5 sectoral reports to look at those in a much wider sense. And I hope that as you respond to this, you can join us in that thinking of where the rich themes of innovation are compatible with a true low-risk approach to hitting our safe climate targets in 29 years' time. Thanks very much.
Thank you, Julian. Right, we'll start with plenty of questions come through. We'll start with one. There's a couple of related questions actually. The first is from James John. When you say that it is now a law to meet 100% emissions reduction by 2050, what are the repercussions of not meeting that law? And I'll give you an associated question to consider alongside that, Julian. From Adam Hodges, I see it unlikely that the practicable large-scale replacements for fossil fuel aviation and shipping industries will be viable by 2050. Is it realistic to assume these industries will cease rather than a change of policy to allow their continued operation?
Yeah, thank you. So looking in the political crystal ball, that was a key question in my mind and even a concern when the Lords debated absolute zero. And I asked it of several of them in one-to-one conversations, and they all said no. They didn't think the law would be repealed or modified because it's got so much political support, and it would be so embarrassing for any politician to try and repeal it. My personal view is that we still haven't quite got it about climate change. We're still talking about it as a kind of dinner party conversation rather than as an existential threat. But the symptoms are growing. And if you look 10 years ahead, I think the rate at which we're getting frightened about the symptoms is really going to change things. And of course, by then, the young people who are the school protesters and the students who are concerned now are going to be in the workplace having an impact. So I think the law is going to stand, and the questions are all going to be about delivery, and the radical changes are going to seem less radical than the threat of not responding.
Okay, thank you, Julian. I have a number of questions on this subject, but I'll go to the most succinct one. So, Sean Spencer asking, do you see a future for the national adoption of hydrogen? Others have been asking in relation to for aerospace or marine to enable ongoing use of those sectors. Yeah,
that's a great question. We excluded it in our planning because it doesn't yet operate at scale, so it's an innovation technology. And the problem that we have with hydrogen is that it's currently 95% of hydrogen is made from methane and leads to emissions. It can be made by electrolysis, as I'm sure the people asking the questions know. So to do so requires that we have an excess supply of non-emitting electricity, or in a more realistic way, that we sacrifice some electricity from other activities and use that to make hydrogen from electrolysis. The round-trip efficiency of doing that is quite poor, so we would have to sacrifice more than we got back from using hydrogen. So pragmatically, I think by 2050, the only way that we could include hydrogen is by accepting a larger cut in the availability of energy for use. So I think that's quite a challenging request. However, its attraction in helping us to balance the grid, to balance the mismatch between the generation of renewables and the periods of demand, is quite significant. So I think it makes great sense that we press on with the most rapid, large-scale experiment with hydrogen as part of our development process. But I don't think we can risk, I think the energy equation just doesn't stack up if we imagine that we immediately replace the natural gas distribution grid with a hydrogen distribution grid as has been proposed. I think we just won't have enough electricity to be able to do that.
Thank you. An interesting question here, actually. You presented some great evidence base for countering the techno-optimism. So the life cycle or development cycle for step change technologies in other sectors, showing this to be decades in the making, and also the 14-year build plan for the Forth Bridge. But a question from Colin Warburton was, what was the overall time for the original Forth Bridge? I think maybe getting to the point that there may be more efficient ways of accelerating the innovation cycle. If you don't know the answer to the direct question, maybe a comment on, could there be a means, a different approach to innovation and validation of new technology that accelerates?
The direct question is a very good pointer, because the original Forth Bridge was built on the back of the Tay Bridge disaster. And it's precisely because things go wrong that we put in place safety laws and laws about public consultation that slow projects down. So we've been doing some very detailed analysis of past energy transitions over all the technologies where we can find data streams. And what we found is that in the early stages of development, there is a period of exponential growth. And I think the slide I showed on wind sort of showed that at the global scale. But it stabilizes once you get to the point that the projects are big enough that they require consultation and permissions and public funding and so on. So although there can be economies of scale in manufacturing, I'm not sure how many economies of scale you can get in local consultation when it's different communities being affected by the different installations. So far, we haven't worked out how to do it. All the big energy transitions have had an exponential period up to, let's say, 5 or 10% of their eventual scale, but then the deployment rate has been linear.
Okay. Thank you, Julian. We've had some questions about supply materials, in particular a question, do we think we can meet the anticipated rising demand for lithium in terms of battery technology, in terms of material availability and processing? More generally, do you see a demand on new materials that enable the green technologies to be a barrier?
Yeah, thank you. I don't know the answer to that, but given the comment I made about criticality at the beginning, we're seeing such a rapid growth in demand. I think it's very likely that we're going to see some constraints there. And people often talk about cobalt and the Democratic Republic of Congo. There are efforts now trying to activate other supplies. And I know that there's been a big EU project on small-scale mining that has revealed the fact that for some of the critical metals, there are new approaches to mining. Most of the critical metals, I think, at the moment are the byproducts of conventional bulk metals. But there are new approaches being developed that allow us to go more directly for the critical metals. So I anticipate that there will be other forms of capacity coming on stream, but the timing question is a good one, and I would be surprised if we don't hit a bump at some point in that.
Got a question related to nuclear. There's been quite a few related to nuclear, actually, and one from Ruffles saying small-scale nuclear reactors could contribute to increasing the electricity supply capacity. Do you see that as being a credible part of an important part of the solution?
It's in the innovation space, so the technology's been proven in the sense that it works on ships. But what we don't know is how the public will react to having small-scale nuclear placed at the end of their street. So I think it's in the bracket of things that we should be trying and trying to get a deployment in a sufficient scale that we can find all the issues with it. I think at the moment we just don't know. And given the extraordinary timescale of Hinkley Point C, I think it's pretty unlikely that big nuclear is going to be making another significant contribution over the timescale that we've got available. But small nuclear is clearly an option that we haven't yet fully tested, and presumably it's one that we ought to be giving a serious chance to.
And what about the conundrum about meeting the scale of investment in offshore wind or potentially modular nuclear reactors without a steel or concrete industry?
How do you make foundations without concrete? I think is probably the number one most difficult question that we've come up with at the moment. With steel, I honestly don't think there is a problem. The industry has been configured assuming that blast furnace steel is good, recycled steel is bad, but that's only because of the economic incentives that have allowed scrap steel to be collected in a rather careless way so that the composition is poorly controlled and it's largely used for making reinforcing bar, which can tolerate higher degrees of contaminants. I think that's all solvable, as for example happens in the US where Nucor is the world leader in steel recycling, and I think 60% of US steel capacity is actually electric arc furnace production from scrap. For cement, it seems to me obvious that the last kilogram of emissions is going to be the hardest one to give up. And as we stand, I think we'll be giving up flying before we give up cement, because it's so difficult to imagine how we can install the renewables without any new foundations.
Okay, thank you, Julian. There's many more great questions coming through. I'm afraid we're running out of time. I'd like to thank you for an excellent talk. Great feedback coming through from the comments from those listening. I think you made the case there for some real challenges and need to innovate in the sectors where we know we need to make an impact. I think it's a great opportunity for the manufacturing and engineering community to really increase the pace of innovation, bringing those technologies that are closer to maturity to deployment, and accelerating some of those that could make huge impacts, such as hydrogen, across a range of sectors. Any final closing comments, Julian, before we wrap up?
No, just to say thank you very much to everybody who's submitted the questions. The IMechE are creating a log of all of those, and what we've been doing since the Absolute Zero report came out is collating all the feedback that we've received, which is rich and fantastic. We'll be publishing a second edition of Absolute Zero at the end of this year, responding to all the feedback and new input that we've received. So at the minimum, I can guarantee that we'll take your questions and comments into account at that point. If we can, we'll try and develop some shorter term responses. And there's also a dialogue page on the UK Fires website where we could try and engage more immediately. So thank you very much for giving up the hour to take part.
Yeah, well, thank you, Julian, and thank you all. And that brings this webinar to a close.